My name is Nisha and I'll be presenting my project which is UV Index Prediction and Safety Advisory System. This work is part of my Artificial Intelligence and Machine Learning course which is PhD 531. The main idea behind this project is to combine environmental data with machine learning techniques to predict the daily UV index and provide personalized safety advice based on that prediction. In this presentation, I'll take you through the motivation, dataset, pre-processing steps, and EDA, model building, etc., etc. We'll see those. So the first question is, why are we predicting UV index at all? So ultraviolet radiations are part of sunlight that has both benefits and risks. So the moderate amount of UV exposure is necessary for UV for vitamin D synthesis, but too much exposure causes serious problems like sunburns, premature skin aging, eye damage, and even skin cancer. It also impacts the agricultural productivity and the health of outdoor workers. So the challenge is that while many weather applications display a UV number, they rarely interpret it. If a person sees a UV is equals to 8, most people don't immediately know what to do with that UV. So the goal of the project is not only to predict the UV index numerically, but also to classify the level of danger from like low, moderate, high, very high, extreme, etc., etc., and to generate safety guidelines automatically. And also, it connects data science with the health awareness, helping users make informed daily choices. So now, for training and testing, I used a dataset obtained from Kaggle, which includes various weather parameters influencing UV radiation. These features are as follows, which are temperature, humidity, atmospheric pressure, etc., etc. There are 13 columns in total, and the target variables are two, which are UV index for the regression task and danger level for the classification task. The dataset covers a variety of seasons and climates, which is important because UV intensity is affected by geographical and seasonal factors. With such diversity, the model learns patterns that generalize well to unseen weather conditions. The relationship between these parameters is intuitive. For example, high temperature and clear skies increase UV intensity, while high humidity, dense clouds, or rain tend to reduce it. So, and this is the sample of my data, which includes six rows from the data. Uh, Once the data set is collected, the first step was to clean and standardize it. So, data pre-processing ensures that the model receives an accurate and consistent input. First, I checked for duplicates and then removed them to prevent any data bias. Then I handled missing values using the mean for numerical columns and mod for categorical ones. Categorical variables like weather type were converted to lowercase and standardized so that similar categories like clear with a capital C and clear with a small c are treated the same. And to ensure consistency, all numerical values were capped in uniform units like temperature in degrees Celsius, wind speed in kilometer per hour, etc. etc. The outliers were identified using the interquartile range method, which is also known as the IQR method. You can see the box plot on this slide that before cleaning, several extreme values were lying far outside the boxes, like these values. Um, these were either corrected or removed to make the distribution more compact. After pre-processing, the data was balanced, complete and ready for analysis. After cleaning, I performed exploratory data analysis to understand how each feature affects UV intensity. So let's look at some of the insights from EDA. So in the first plot, UV index increases non-linearly with temperature. Like there's a sharp rise around 25 degrees Celsius and like after 25 degrees Celsius, which then tends to plateau, showing that temperature alone cannot infinitely increase UV. It saturates UV. And then next we have the humidity graph, which shows an inverse relationship. Like beyond 70% humidity, UV levels drop sharply because water vapor scatters and absorbs sunlight. And then we have wind speed, which has a weak correlation because clearer, drier days with moderate winds often show slightly higher UV readings. Visibility turned out to be an excellent indirect feature too, because low visibility often was due to haze or dust, which later corresponded to lower UV penetration. So the precipitation chart also demonstrated that heavy rainfall or thick clouds, like about 40% precipitation, drastically reduced UV. And finally, seasonal analysis showed a consistent peak in late spring and early summer, which was influenced mainly by solar angle rather than temperature. So these EDA results help select the most impactful features for the predictive models. To improve the performance, I created a few engineered features that capture complex relationships more clearly. So the first one is feels like temperature, which is the formula is this is the formula for feels like temperature. So it combines temperature and humidity to represent perceived warmth. This helps the model handle cases where high humidity makes moderate temperatures feel like hotter. So the second derived feature is sky opacity, which multiplies precipitation with cloud cover. It it quantifies how much sunlight is blocked before reaching the ground, a key factor for UV intensity. I also applied cyclic encoding for a season column using sine and cosine transformations. This preserves the natural continuity of seasons, like from winter to spring to summer to autumn, instead of treating them as separate categories. Finally, all numeric features were standardized using standard scalar, ensuring uniform scales and preventing bias towards larger magnitude variables. These engineered and scaled features gave the model better sensitivity to atmospheric variations and improved predictive accuracy. With this data prepared, I divided it into 80% training and 20% testing sets. Two main tasks were defined: regression and classification. For regression, predicting the UV index value, I used a random forest regressor. For classification, for predicting the danger level category, I use a random forest classifier. And I also compared them with XGBoost and Light GBM models, which are gradient boosting algorithms known for handling tabular data efficiently. And then I use hyperparameter tuning, um, uh, which systematically tests combinations of parameters like tree path, a number of estimators, or learning rate to find the optimum configuration. And then finally, best models were cds.pkl files using joblib for easy integration with the dashboard. Um, this is the diagram illustration of pipeline, data input, pre-processing, and then model and then prediction. Once the data is trained, each model was evaluated on the testing dataset. For regression tasks, the random forest regressor delivered the most accurate predictions with the low mean squared error and minimal variance. You can see the values here for ME, RMSE, and R squared score. For the classification task, we evaluated performance using a confusion matrix. In this heat map, the darkest cell along the diagonal, which is this cell, represents correct predictions. The model performs exceptionally well for the high and very high categories, with only minor confusion between adjacent levels like moderate and high. A common and acceptable overlap is there because UV categories are naturally continuous instead of being discrete. Both models demonstrated strong accuracy, consistency, making them suitable for real world use. After achieving accurate predictions, the next challenge was to make them useful and understandable for the public. So I aligned the model outputs with the World Health Organization's UV index standards, mapping each numeric range to a danger level and safety advice. So these are the levels 0 to 2, 3 to 5, etc., etc., and so on. So by integrating these thresholds, the system instantly converts numeric UV prediction into a clear recommendation. This bridges the gap between data science and practical day-to-day safety. Now we have a dashboard. So to make the system accessible, I built an dashboard using Streamlit. It allows real-time users input and instant model output. On the left panel, on this panel we can input the data, and then these are the predictions. This is the result which will be shown. um, Once we submit the data, the dashboard uses the trained models to generate the predicted UV index, the danger level classification, and personalized safety advice. As you can see in the screenshot, there's also a colored coded progress bar from, like, for green for low, yellow for moderate, orange for high, and etc., which is making it understandable. The goal was to keep the design clean and minimal so that even a non-technical user can interpret the result without confusion. Um, then, to enhance the usability, I extended the system to generate a 7-day forecast. Using the same trained model, small simulated variations in weather parameters created a realistic prediction for UV intensity for each upcoming day. On this slide, you can see how a line chart, this line chart representing the forecast. The upward and downward trends mimic daily changes, helping users to spot days with potentially high UV risk. For example, if the forecast shows a peak midweek, users can plan outdoor tasks or tip on safer days. This forecasting ability turns the dashboard from static predictors into a decision support tool for health and activity planning. So now I'm going to show you the dashboard, which is this one. Sorry, this is the dashboard. So these are the active inputs which we can provide by ourselves, and these are the results. So I'll enter a random value. Let's say we'll enter 25, and we'll change this value to 10. Then we'll let's say make the precipitation to a higher value, and then uh, let's change the pressure a bit. Then we'll predict the UV index. So as you can see, this is the predicted UV index, and this is the danger level, which is high, and this is the guideline which is provided to the user. And then this is the relative UV intensity, which is also shown here, which is 44.4%. And then there is a 7-day UV forecast. This is a line chart which we were talking about earlier, and this line chart. This is the 7-day forecast. So let's just do this for another value. Let's change the value to 45, and let's just change humidity, decrease the humidity, and now we'll predict the UV index. So this is 9.06, which is very high, and so this is saying that SPF is should be greater than 50%, and we should seek shade. And this is the predicted UV index for the upcoming week. So now getting back to the presentation. I've shown you the dashboard. Now let's talk about the future and results. So to summarize the results, the model achieved high accuracy in both regression and classification. The project successfully delivered an end-to-end pipeline starting from raw data through cleaning, feature engineering, model training, and finally deployment in an interactive dashboard. This approach demonstrates how AI can directly support environmental safety and public health awareness. So in the future, there's a lot of scope to expand this work. This next steps can be like integrating this with live weather APIs so that dashboard updates automatically. So deploying it on Streamlit Cloud or AWS to make it accessible online, and adding geolocation-based predictions to users instantly to get results for their current city where they are living. These improvements will transform the system into a real-time location-aware UV advisory platform. So this brings us to the end of my presentation. Through this project, I've learned how every stage of learning, machine learning from pre-processing to deployment contributes to building a complete and reliable solution. It taught me the importance of data quality, feature engineering, etc. And most importantly, it showed how AI can make a positive social impact in promoting sun safety awareness and helping people take preventive actions. So thank you for listening. I hope this presentation gave you a clear understanding of my project and how machine learning can be applied effectively to real world environment and health challenges. Thank you.